Morning, thanks for joining. That's Joe standing next to me, and I'm Nico, and we work for Microsoft at the Security Response Team, the MSRC, and we're here today to talk about Hyper-V and some of the outstanding vulnerabilities we've seen. So you guys, you might be wondering why we are doing that, why we are talking about vulnerabilities in our own product. There are various reasons for that. One of the reasons is that we've got an outstanding bug bounty. So before joining Microsoft, I used to be a bounty hunter, and in my own opinion, right now this is one of the best that we have. Look at these figures. For an RC in a kernel, we will give you $200,000. And if you manage to exploit that, that will be another 50,000 more. So why this payout? Well, because exploiting, finding bugs in Hyper-V is not trivial. It's hard. It's complicated. It takes a lot of time to ramp up. And besides, there are not that many blog posts available around there. Not many vulnerabilities publicly described. And for all of this, we thought that it would be great for us to stand here before you today and talk about the internals of Hyper-V, which is what Joe is going to do in a second. And I'll come back later and I will show you some great bugs that we've seen in Hyper-V. All right, Joe.
Thanks. So one thing I'd like to note is we get questions sometimes from people who look at our bounties and they say, hey, your bounty says that you'll pay up to $200,000 or up to $250,000, but how much am I really going to get? And just to provide some clarity for you guys, unless we have a really good reason not to offer that maximum bounty payout, we pay the maximum. If you find a good bug and you exploit it in Hyper-V that's in the kernel of the hypervisor, you're probably going to get $250,000. So the first thing we'd like to do, as Nico mentioned, is we would like to give you a little bit of an overview of Hyper-V's architecture from the perspective of a security researcher that is just interested in going and trying to find guest-to-host escape bugs. So if we look at Hyper-V from a really high level, you can see that at the top here we have the hypervisor, and down below we have a number of what we call partitions. In Hyper-V, a partition is how we describe the logical unit of isolation that we use to isolate different virtual machines from each other. Now, partitions get isolated in a few ways. The first way that they're isolated is the hypervisor uses the extended page tables to control what physical memory each partition actually has access to. And another way that isolation is provided is the hypervisor is able to receive intercepts or traps whenever certain instructions are executed by a partition. So for example, the hypervisor can intercept any attempt by a partition to execute in or out instructions, which are used to communicate with I/O ports. So by doing this, the hypervisor can really effectively prevent a partition from having any access to hardware whatsoever, and also from having any access to other partitions on the system. So you can see we have these dotted purple lines on this slide, and this is just kind of to illustrate that none of these partitions have access to each other's physical memory, and they also don't have access to the physical memory of the hypervisor itself. And that brings me to my next point. Some of y'all might be familiar with other virtualization stacks like KVM, for example, and in some other virtualization stacks, the hypervisor is a component that it lives inside of the kernel of the host operating system. And that is not how Hyper-V is designed. In Hyper-V, the hypervisor is a standalone binary that lives in its own physical and virtual address space. So none of the partitions have the ability to mess with its memory. The hypervisor in Hyper-V is not really responsible for a lot of interesting functionality from a guest-to-host attack surface perspective. It's responsible for configuring the extended page tables. It's responsible for some other hardware-specific or virtualization-specific hardware configuration. And it will end up handling things like intercepts or traps for things like a hypercall being made, which is the system call of the hypervisor world. Or it will handle traps if certain privileged instructions are attempted to be executed. But most of the really interesting attack surface isn't in the hypervisor, so I wouldn't recommend that you spend a whole lot of time there. Let's move on to the root partition. Now, I mentioned previously that all of the partitions isolated from each other. The physical address space is isolated from each other. And that's actually not quite completely true. There's one special partition in Hyper-V, which we call the root partition, and this is where the host operating system runs. The root partition has access to the physical memory of all of the other partitions on the system. And that's because the root partition is ultimately responsible for managing all of the virtual machines that run on the system. It also has access to all of the hardware, so it can talk to the network card, the video card, etc. And because it has this special access, it's ultimately responsible for providing a number of services to all of the other partitions or virtual machines that run on the system. Most of the interesting guest-to-host attack surface in Hyper-V lives inside of the root partition. So that's where you should really spend your time if you want to try to find these kind of bugs. And last, we'll just mention the guest partitions, which is any partition that is not the root. These partitions really do not have access to the physical memory of any other partition. They only can access their own physical memory. They have no access to any of the hardware on the system. They can interact directly with the hypervisor by making hypercalls, but there's a very limited set of hypercalls that guests can make. And they have no ability to communicate with any other partition except for the root partition. So in Hyper-V, there really is no direct guest-to-guest attack surface. All of the attack surface is either guest to hypervisor or guest to host. All right, so before we move on, I want to give you guys a little bit of terminology. When we're talking about physical memory in virtualization, it can always be a little bit tricky because the hypervisor uses the extended page tables to control what physical memory all of the guest partitions can see. So in Hyper-V, we use the term system physical address to refer to the real physical address of memory. And we use guest physical address to refer to the physical addresses that the guests are seeing. And the hypervisor uses the extended page tables to map guest physical addresses to system physical addresses. We also have a concept in Hyper-V called a guest physical address descriptor list, or GPADL. If any of you are familiar with Windows kernel programming, this is conceptually identical to an MDL, or a memory descriptor list. All that a GPADL is it's a small header, and then it's followed by a list of guest physical addresses. And guests can use a GPADL to describe a range of physical memory that they want the host to do, certain operations on. And when we're looking at Hyper-V and we're trying to look at different components that the guests can attack, those components primarily fall into three categories. The first is a virtual device, or what we call a VDEV. This is either an emulated device or a para-virtualized device, and it lives inside of user mode in the host operating system. Next, we have a virtualization service provider, or VSP. VSPs are para-virtualized devices that live inside of the kernel of the host operating system. And finally, we have integration components. And from the perspective of someone who's just trying to find guest-to-host bugs, an integration component is basically identical to a VDEV. It is a component that is hosted in user mode on the root partition, and the guests can communicate with it over specific communication channels. So there's really not any difference between these and VDEVs. Now, I had mentioned before that the root partition is responsible for providing a number of services to the guest partitions. And as you can probably imagine, this is necessary because the guest partitions have zero access to hardware. So unless someone provides them with storage and networking and other stuff like that, a guest partition wouldn't even be able to boot. We have a few different types of devices that end up being exposed to guest partitions. First, we have emulated devices. So we have an emulated network card, video card, motherboard, serial port, etc. There's a whole list of these things. And the emulated devices literally emulate super old hardware that basically every operating system in existence knows how to use. So the network card is like a 25-year-old network card that operates using I/O ports. As you can imagine, doing hardware emulation is really slow. And for certain things like networking or storage, you need super, super good performance. And so that's where the para-virtualized devices come into play. We have a para-virtualized network stack, storage stack, video stack, and a para-virtualized PCI device. And finally, we have sort of a grab bag of other functionality that the hypervisor root partition needs to provide to guests. This is things like you need to provide the BIOS firmware that the VM is going to boot off of. You need to provide live migration support. You need to provide the ability to commit and decommit physical memory from the virtual machine while it's running if you want to have dynamic memory. We have a number of integration components. These typically do things such as provide the host's time to the guest so that the guest knows what time it is. Or there's an integration component that allows you to gracefully shut down the virtual machine from the Hyper-V interface without having to go and actually log into the virtual machine and do a shutdown from the virtual machine itself. And then we have Hyper-V containers, which we're not going to talk about much in this talk, but it's worth noting that there's also some specific functionality that's provided if you're running a container. So if you're running a Windows container, we have an SMB server that ends up being exposed to that Hyper-V container. Or for a Linux container, we have a Plan 9 file server that's exposed. It's also worth noting that Hyper-V has 2 generations of virtual machines, and you select what generation you want when you create the virtual machine. Generation 1 VMs have a significant amount of emulated devices exposed to them, whereas Generation 2 VMs have almost no emulated devices exposed to them and pretty much exclusively use para-virtualized devices. Some of these services are also not mandatory under any Hyper-V configuration. So live migration is an example of a service that Hyper-V can provide to a guest, but doesn't necessarily need to. If you're never going to live migrate the guest, then that is just not an attack surface. So Hyper-V really is designed with the principle of least privilege in mind. As I noted before, the hypervisor itself doesn't really have a whole lot of functionality in it, especially from the guest to host perspective. We put all of that functionality into the root partition where possible, and when we're looking at where we put it in the root partition, we prefer to put functionality in user mode unless we can't for either performance or just architectural reasons. But as a guiding principle, we always try to put code in user mode. I thought it would be useful to give you a more componentized view of where some of this attack surface lives in Hyper-V. Hyper-V is split on the root partition is split between kernel mode and user mode components. In the kernel, we have the VM switch, which provides para-virtualized high-speed networking, and we have the store VSP, and there's a couple other drivers, but they all chain up to store VSP, that end up providing para-virtualized high-speed storage. We also have our para-virtualized PCI stack in the kernel, which is there mainly for architectural reasons. The PCI stack is actually not usually used for virtual machines. It's mainly there to support scenarios such as SRIOV, where you might have a piece of hardware that is virtualization aware, and you want to attach a virtual function from that hardware directly into a virtual machine. That's the kind of functionality that vPCI supports. Then we have the VM bus, and we're going to talk more about the VM bus a little bit later, but VM bus is the high-speed communication channel that para-virtualized devices use to communicate between the guests and the hosts. We have WinHVR.sys, which is the kernel hypervisor interface, and this is effectively the kernel 32 of the hypervisor world. It just contains functions that wrap hypercalls so that it's more convenient to do hypercalls. And last but certainly not least, we have the virtualization infrastructure driver, or the VID. The VID is a pretty important component for Hyper-V, but it doesn't actually contain an incredible amount of direct attack surface. The VID is the primary driver in Hyper-V that communicates with the hypervisor itself. So if you need to create a new virtual machine, it's ultimately going to be the VID that makes the hypercalls to the hypervisor to tell it to make that new virtual machine. The VID will be responsible for depositing physical memory into those partitions so that the virtual machines have physical memory they can use to run. The VID is also responsible for doing things like registering with the hypervisor that some user mode component wants to receive notifications when a particular I/O port is accessed. So all of this state keeping is really done in the VID, even though the VID isn't really direct attack surface. Now, on the user mode side of things, Hyper-V has a number of processes that run, but from the guest to host attack surface perspective, there's only one process that's super, super important, and that is the VM worker process, or VMWP. One really cool characteristic of the VM worker process is that there is one worker process per virtual machine running on the system. And what this means is that if you manage to find a denial of service bug in code that's in the VM worker process, you'll be able to crash the VM worker process, but you won't be able to crash the entire host operating system, which means that that denial of service bug will only denial of service your VM. It's effectively a self-DOS. It doesn't affect anyone else running on the system. So that's one great reason that we really like to put code in the VM worker process. It makes the whole system more robust. Now, inside of the VM worker process is where basically everything lives that hasn't been explicitly called out as either being a hypervisor or kernel mode component. This is where all of the virtual devices live. This is where all of the integration components live. This is where, if you're running a container, this is where the SMB server or Plan 9 file server lives. And then there's also a bunch of what I would just characterize as general machinery that runs inside of the worker process. This is stuff that maybe makes a VDev's life easier. For example, if a virtual device wants to register for notifications when a particular I/O port is hit, that virtual device will call into this subcomponent in the worker process called the VND. And the VND will ultimately communicate with the vid in the kernel and tell the vid that it wants to have this notification made. So by doing this, the virtual devices don't need to all individually talk directly to kernel components, directly to the vid. They can just talk to the central component in the worker process and it will do things for them. Now, some of you might be wondering, this is all great, but how do I actually talk to these various components? How do I talk to the VM switch? How do I know how to speak the VM bus protocol? And I've got awesome news for you. Since the Linux operating system can run as an enlightened Hyper-V guest, all of the source code for this stuff, the client-side source code, is checked into the Linux source tree. So if you want to know what a VM bus client looks like and you want to know how that protocol works, you can just go and look in the Linux source tree and the VM bus protocol is implemented there. If you want to know how to talk to the VM switch, you can just go and look in the Linux source tree and we have a VM switch client that's checked into Linux. So it's all there waiting for you. All right. Now, as much as I would love to just describe every single different component that Hyper-V has that's attack surface, we don't have time to do that. And so I thought it would be more useful to walk everyone through what some of these communication channels look like between the guest and the host, so that you can use this information to go and find all of the different pieces of attack surface in Hyper-V. So we'll start with the hypervisor, but we're not going to spend too much time here because, as I've said before, this is not where most of the interesting attack surface is. The hypervisor's most direct communication method with the guests are hypercalls. There are two ways, really, that hypercalls can have parameters passed to them. You can either put the parameters directly in registers, or you can pass a address, a guest physical address, to some guest physical memory, and the hypervisor will go and do processing on that physical memory. There's a very limited set of hypercalls that are exposed to guests. It's mainly to do things like faster enlightened TLB flush. But there's no hypercalls that would do like device emulation, for example. You can also communicate with the hypervisor somewhat indirectly through faults. So if your virtual machine has a triple fault, that will end up being handled by the hypervisor. If there is an extended page table fault, you try to access some physical memory that is not mapped in the EPT, that will trigger an EPT fault. And this is actually how MMIO can be implemented in the hypervisor. The hypervisor can see that you're attempting to access some physical memory page that is marked as being an MMIO emulated range. And so when it handles that fault, it knows, oh, I actually just need to pass this on to the vid to do processing. You can also indirectly communicate with the hypervisor by trying to execute certain instructions, like CPU ID, or as mentioned before, the in-out instruction for doing I/O port reads and writes. The hypervisor will intercept attempts to execute those instructions and will end up emulating them, either directly in the hypervisor or it will pass it down to the host to do emulation. Similarly, you can do the same thing for certain privileged register accesses. So you can intercept guest attempts to write to the CR4 register, for example, or to MSRs. And the last one I'm going to mention, just because you might run into this and end up wondering what the heck you're looking at, are overlay pages. An overlay page is not really guest to host attack surface. It's just a way that the host or the hypervisor can forcibly map some page of memory into the host or into the guest's physical address space. One reason that Hyper-V does this is it will map in a page into all of the guests, which contains the instructions that you need to execute to make a hypercall. All right, let's move on and talk about kernel mode communication channels. By far the most important communication channel for kernel mode is the VM bus. And once again, we're going to talk about this in just a couple of slides in more detail, but suffice to say this is a high-speed communication channel, and this is used by all of the virtualization service providers that live in the kernel. There are also extended hypercalls. An extended hypercall is simply a hypercall that the hypervisor forwards directly down to the vid to handle. There's very few of these, and they don't do things that are super interesting, but you might run into these, you might want to look at them, so I'm noting them here. We also have apertures, and these are used primarily by user mode, so I'm going to talk about them more on the next slide, but it's also possible to use them in the kernel. And the kernel can also be communicated with somewhat indirectly, once again, through intercept handling. So if the hypervisor receives an intercept for some instruction that it needs to emulate, for example, like an IO port write, it will forward that on down to the vid in the kernel. And the vid will look at that and decide where it needs to be forwarded to, or if it just be rejected. It's a decision maker. So it's not really direct attack surface, but you will end up triggering code paths in the kernel, and so it ends up being somewhat of a communication channel. And lastly, we have user mode. Now, user mode is where all of the device emulation happens, so we end up having a lot more direct communication channels in user mode components. The first one is IO ports. User mode components can register that they want to receive notifications when particular IO ports are read or written, and they can then use that to do hardware emulation. And similarly, components can register for notifications when particular physical addresses, guest physical addresses, are read or written to, and they can use that to emulate MMIO access. Then we have the VM bus. The VM bus is also used by user mode components, although the access happens through either VM bus pipes or VM bus sockets, which we'll talk about in a second. Then we have apertures in user mode. Now, an aperture is how we describe mapping a guest physical address into the virtual address space of the host. So in the case of user mode, you map some guest physical address into the VM worker process's virtual address space. And this allows you to read and write that guest data. Now, you need to be super careful when you do this, because the memory is still mapped inside of the guest, which means that while you're doing processing on that memory in the host, the guest can be going and modifying that memory from underneath you. So this is an area where if you're not careful, you can end up with dangerous double fetch conditions. And the last one we have here are read and write notifications. Now, when I first saw these, I was fairly confused as to what the difference was between a read and write notification and just doing MMIO. There's one key difference here, and that is that while read and write notifications do allow you to get notified when memory is read or written to, just like MMIO, it does not advance the instruction pointer, which means that you cannot do emulation. You cannot provide the guest with some value that they are trying to read. You are just simply notified that the guest is indeed reading from this page of memory. And one reason why you might want to use functionality like this is if you're doing live migration. You're copying all of the guest physical memory over the wire to another server. And at some point, you just transfer execution over to that host. But the virtual machine is running while you're copying this memory over. And so Hyper-V needs to be aware if some page of memory changes in between that copy operation and execution being transferred over to the new host. And so Hyper-V can place a write notification on a block of memory after it's been copied, and then Hyper-V can mark that memory as dirty if it gets written to. And then Hyper-V knows, oh, before I transfer execution over, I need to recopy these pages of memory. So that's why we have read and write notifications. All right, now I promised that we would talk about VMBus, and that's what we're going to do now. VMBus is a communication channel that is built around shared memory. It all starts with the host making a channel offer to the guest. When the guest accepts that channel offer, the guest will indicate to the host a set of guest physical addresses that the guest would like to use to establish that VMBus channel. The host will take those guest physical addresses and map them into its virtual address space. And so now the situation you're in is one where both the guest and the host have a virtual address range that maps the exact same physical memory. So the guest can write some data into this memory and then signal to the host that there's a packet waiting, and the host can go and directly access that packet. Once again, the Linux integration drivers fully implement the VMBus, so if you want the nitty-gritty details of how the protocol works, you can go check it out there. However, you don't actually need to know how the protocol works to attack components that use VMBus, because you can just go and modify the client implementation for the components, like for virtual storage, you can modify the virtual storage client, and the virtual storage client in Linux will just use VMBus automatically for you. You can just ignore the implementation details of it. Now, no components in Hyper-V actually directly use VMBus. They all go through abstraction layers. In the case of the kernel, they go through the kernel-mode client library, or KMCL. And in the case of user mode, they go through either VMBus pipes or VMBus sockets. KMCL, which is what all of the virtualization service providers use, is really built around callbacks. When you establish a VMBus channel, you provide it with a number of function pointers to call when certain events happen. And predictably, one of those events that can happen is you've just received a message from the other end of the KMCL pipe. Now, when that message is received, even though the message came in over the VMBus inside of this shared memory region, we actually copy that data outside of the shared memory region and into the kernel pool before delivering it to the KMCL client. The reason we do this is because we want to avoid double fetch conditions. So we make a safe copy of the data before passing it along. However, there is one way that this can be done unsafely, and that is with the external data mechanism. Guests, when they send a VMBus packet over the wire, can attach a GPADL, which is that guest physical address descriptor list, to the packet that they're sending. This is just, it contains a list of additional guest physical addresses that contain additional data for processing. The host has to map this GPADL explicitly, but once it maps it and starts accessing it, the host needs to be very careful to avoid double fetch situations, because that memory is mapped in both the guest and the host at the same time. Now, at the end of this slide deck in the appendix, and I'm going to publish the slides, we have gone and documented a whole bunch of the different interfaces that Hyper-V components use to do things like make channel offers, do I/O port reads and writes, etc., so that you know what sort of symbols to go and look for if you want to find this attack surface. This right here is one example of how KMCL is established. This function highlighted in yellow is the function signature for a KMCL message received callback. And there's two really important parameters here. There is the buffer and the buffer length. And predictably, the buffer is a pointer to guest supplied data. So this is fully attacker controlled. And buffer length is the length of that data. All right. So the next channel we're going to talk about are VMBus pipes. This is the primary way that user mode components use VMBus. VMBus pipes, once again, start with the channel offer. There are two functions, which I've documented here, that are used to make that channel offer. And they return a handle to a VMBus pipe. The way you interact with VMBus pipes is exactly the same as with normal named pipes on Windows. You call read file and write file, or you can use I/O completion if you want to do asynchronous operations. And that when you're doing the asynchronous operations, Hyper-V has some helper classes that they tend to use, which I've noted here. So you'll want to check that out if you're trying to look for components that are using asynchronous VM bus pipes. And finally, I'm going to talk briefly about I/O ports and MMIO entry points. I/O ports and MMIO ports once again start with a registration event. So the component will either say, I want to receive I/O port notifications for these particular I/O ports, or I want to receive MMIO notifications for these particular guest physical address ranges. In the case of I/O ports, whenever that I/O port is read or written to, one of these two functions noted here will be called. It contains the I/O port address, the size of the access, and a buffer either containing the data being written or a buffer that you need to populate with the data being read. And accordingly, for MMIO, there's notify functions there, notify MMIO read, notify MMIO write, which do similar things. Now, every VDEV that uses I/O ports or MMIO ends up implementing these functions. So if you want to find these entry points, you can just open up your debugger, attach it to VM worker process, and do a symbol search for any component that has notify I/O port read in in its symbols. And you'll be able to find all of the VDEVs that implement I/O port read emulation, as an example. All right, so this wraps up my portion of the talk. What I'm hoping that you've got from this is that Hyper-V has a number of services that it needs to provide to the guest VMs. And there's a number of entry points which a guest VM can use to trigger code, different code paths in the Hyper-V host. Now, Nico is going to show us how to apply this knowledge to some real Hyper-V bugs that both we and external people have found, just to give you examples of how to actually use this information.
Yeah, thank you, Joe. That was just super interesting. So let's see if we can be a bit more practical now. So before even we thought about doing that talk, we were asking around us why it was so hard to find bugs in Hyper-V. And one of the most common replies that we have was, Nico, you don't realize you've got access to your bug database, you've got access to your source code. We don't even have access to symbols. And that's a very good point. So I can tell you today that this is sorted. Since April this year, there are around 40 PDBs available for Server 2016 and Windows 10. They don't cover the entire set of components, but there's definitely enough for you to start reverse engineering. So yes, let's do that. Let's start reverse engineering and let's find bugs. So we've selected there's 5 vulnerabilities. Why these in particular? Well, first of all, they are all fixed. Yeah, no way, absolutely no way we can talk about something that is unfixed here. Second, as I just talked about the symbols, all the affected components here have a PDB. So you can actually reverse engineer that component and figure out what was the initial vulnerability. Third, some of these bugs have been externally reported, and this is great because we can explain you what was the methodology of the finder, how he managed to find that bug, so you can actually do the same and try to find other issues. And last point, crucially, these bugs are easy to explain. We've seen incredibly complicated bugs, and these bugs, we can't just talk about them here. They are too complicated. But still, if you find them, send them to Joe. He'll love them. So just to talk about, just to take back Joe's slides, so this is what I'm going to talk about here. So 2 issues in the kernel and a couple of other issues in the VDEV. The first issues I'm going to present affect the VM switch. So Joe quickly talked about the VM switch before. So what is this? Well, it does a lot of things, but in a very few words, this is what provides network connectivity to the guest. This first issue was found by Peter Lavati from Tencent. And it's, unfortunately for us, amazingly simple. There is a function in a VM switch that takes a string taken from a packet sent by the guest, and this function just assumes that the string is null terminated. So what happens if the guest sends a packet with a string without any null character? Well, if you put the special flags on VM switch, then the function will just run out of bounds while processing that string, and it will just crash the kernel. That's a great bug. And for a bug like this, we would pay right now $15,000. However, we would pay this if you can give us a POC, a proof of concept. So what did Peter do at that moment? Well, he, as Joe mentioned, he used the Linux drivers. So he first figured out how things worked there, and then he quickly put together a fuzzer. And since, as I just told you, this issue was so simple, after a few iterations, he managed to hit the code and quickly figure out what was going on. So what he provided us was a function that we could just put inside the VM switch code, the Linux drivers, and just run ifconfig from a Linux VM, and that would send the malicious packet and crash the host. That was a great bug, so thanks, Peter, for submitting that to us. If you try to reverse engineer that bug for example, extract the vulnerable function, you won't see a direct relationship with the VM bus. This is because the packet is processed asynchronously. So the VM switch takes that RNDs packet, it put it into a queue, and then only when it has times, it will process it. So look at the stack trace, and if you want to debug it, put the breakpoints there, and you'll see what's going on. Just to conclude on VM switch, there were 3 other bugs found by Kostya Korchinski from Google 2.5 years ago. They are described, the source code, the proof of concept, is there, and it's available on the internet. And also, go check out Jordan's talk tomorrow. It's on VM switch, and it's great. Let's move on to another kernel component, VPCI. What's that thing? Joe quickly talked about it. So basically, you've got your guest, and you want the guest to talk to the PCI component. It's going to use that component. So for example, you want the guest to use your very latest graphic card. This is the component that is going to be used. So the vulnerability I'm going to talk about now was found by our virtualization security team. It's an internal team at Microsoft. So we are hackers. So the PCI thing is handled by VPCI VSP.sys. But we are interested by entry points. We are interested to know how the guest and the host communicates. In this case, they are using a function called channel process packet, which is a big switch. So the guest sends a packet to the host, that packet is processed, and a response is returned to the guest. For certain packets, and especially here the interrupt message packet, you could enter a certain code path where the guest was supposed to return, the host was supposed to return an object back to the guest. If you look at that code, the first thing that you might notice is that the return packet, the return buffer seems to be correctly initialized. However, what is not done here is this translated message object, which is a stack buffer. This one is not correctly initialized. As you can't, if you quickly reverse engineer the function that is supposed to initialize it, you will see that this function only initializes it if no errors happen. So here, the idea is to cause an error during that function, which will return a status, and the function won't initialize this buffer. So in the end, this results in leaking the 10 bytes, 16 bytes in decimal of stack data from the kernel to the guest. For a bug like this, we would pay $25,000. But you need to provide us with a proof of concept. This is very important. So here, what I'd suggest you can always use the Linux drivers. This is perfectly documented. You can quickly figure out how they work and try to repair your own packet. However, what I would suggest you here is just to put some breakpoint in FDO communicate protocol in a guest VM. This is where the handshake happens with VPCI. So what you can do is just look at this function and see how the packet is exchanged, and then you can just put your fuzzer and try to get some bugs. This was a good bug, so thanks for that team for finding it. We stay with the VM bus, but this time we've moved to the worker process. It's important to notice that the VM bus doesn't only give data to the kernel, it also provides data to the worker process. So this bug I'm going to talk about was found in the synthetic video driver. So the synthetic video component, sorry. So what is that thing about? It's basically what is handling the screen resolutions to the guest. So this component, this particular component, is handled in VM UI devices.dll, as well as other components. So go check this out, symbols are there. And again, we are hacker, we're interested by communication, so here it's very easy to audit. Actually, there is a function which is called onMessageReceived. It's, as its name indicates, it received a message from the guest, processed it, and then returned a response to the guest. The bug here was happening under certain condition. It was possible to reach a certain code path with a specific boolean set to false, where an object would be initialized on the heap, but only part of its field would be initialized. So in the end, as you can see here, you would allocate almost 90 bytes in X on the heap and only initialize 9 of them, which would lead to a massive memory leak. For bugs like this, if you can find a repro, we would give you 15,000 USD. And if you try to reverse engineer the patch, you'll see that there was another variant from that vulnerability in another function. And so if you had done this research, you could have easily netted 30,000. How to write a POC for that? Again, it's easy. All the communication is done in hypervideo.sys. So the best way for you would be just to put a breakpoint where the handshake happens and just try to replay your own packets. One thing I haven't said is that we don't necessarily need a driver. You can always send us a Windybug script, for example. For example, this vulnerability was very simple to trigger. So you could, for example, provide us with a script that would just alter some fields in memory, and that would be enough for us. We just need something that is easy to reproduce. As long as it works, as long as it can save time, you'll get the bounty. So now, let's move to the intercepted IO vulnerabilities. Joe, I believe you want to talk about this one. That's your baby.
Yeah. So this was an interesting vulnerability in handling MMIO emulation. Now, as we talked about before, when a function receives a MMIO read request, that virtual device is responsible for providing data back to the guest in response to that read request. And while this function, if you look at the definition that I provided earlier, has a return code indicating if it succeeded or failed, it turns out that that return code is ignored. You always must populate the read buffer, because no matter what, the contents of that read buffer get copied back to the virtual machine. And so this vulnerability actually manifested itself in a couple of different virtual devices, where they would have air conditions, like this air condition here, which is difficult to read, but effectively what happens is the virtual device says, if the number of bytes being read is not 4 bytes, then return, and it doesn't populate that buffer. So if you issued an 8-byte MMIO read request to this virtual device, then you would get 8 uninitialized bytes of stack memory returned to you. And it was actually kind of nice. It turned out that in this case, the memory that would be returned was very consistently a pointer to an object on the heap. So that'd be pretty useful if you were trying to use this to break ASLR. And once again, a bug like this, if you find it and report it to us, will net you $15,000.
Yeah, great bug. So last bug we're going to talk about is actually your favorite. So this one happened in the storage component. The storage component is used by, for example, the floppy or any ID device. So this component specifically listens on the ports 1F0 to 1F7 and 3F0 to 3F7. I stick with the first range here. So the ports 1F1 to 1F7 are explicitly used to change the internal state of a component. But port 1F0 it's doing something completely different. It's actually writing data to a buffer. And the bug here was in this data function. It was possible to manipulate the internal state to use an internal offset that could be arbitrary control. And so in the end, that would give you almost an arbitrary read and write primitive on the heap. This is a critical bug. This is actually one of the best bugs we've seen. This bug has been anonymously submitted to us, and I've got the pleasure to tell you that so far this is the bug that has netted the most, actually $150,000. The bug, the finder originally found it just by fuzzing, but it turned out that once you've reduced the proof of concept, it's just a series of out instructions sent to this port. It's simple, it's efficient, and we want bugs like this. So please send us more. Joe, any closing thoughts?
All right, thanks for that, Nico. So we don't have many closing thoughts for you here. We hope that this has been a super informative presentation for you. We hope that you guys can take this information and use it to find bugs in Hyper-V. And of course, we really hope that you send us those Hyper-V bugs that you find, because we'll pay you a bunch of money for them and get them fixed. As we noted earlier, Jordan from Microsoft is giving a talk tomorrow on Hyper-V exploitation. So if you are interested in Hyper-V and want to get more information about it, you should definitely go and check his talk out tomorrow. It's at 3:50 in Lagoon GHI. So that's all we got for you, and let us know if you have any questions. We can answer questions here, and you can also just shoot us emails or talk to us on Twitter if you have questions after the presentation. So thanks for your time.